Okay.
Okay, welcome everyone to the NE Research Seminar. For those who don't know me, I'm Jason Cole. I'm assistant professor in the department. I'm going to be the host today. It's my great pleasure to introduce today's seminar speaker, Mr. David Gandy. David is not a stranger, no stranger to us. He's State alum. Graduated what, 35 years ago?
Long time ago.
Sorry, give that. Mr. Gandy is a senior technical executive in EPRI's EPRI materials area, where he's responsible for technical oversight of major projects on powder metallurgy, advanced welding, additive manufacturing, Gen 4 alloys, and next generation corrosion wear resistant alloys. Mr. Gandy has 37 plus years of demonstrated leadership and excellence in materials, advanced manufacturing, and welding technologies, supporting the power industry and the development and implementation of advanced light prediction methodologies for boiler, steam and gas turbines, reactor pressure vessels, and heat recovery steam generators. Prior to his current role, Mr. Gandy managed EPRI's technology innovation program, where he was responsible for promoting innovative, exploratory, and strategic technologies across the institute to accelerate the adoption of these technologies within the electricity industry. Mr. Gandy received his Bachelor of Science degree in Material Science and Engineering from NC State University. He currently holds 13 U.S. patents and authorized over 260 journal articles and technical reports. He is recognized as the ASM International Fellow. He's a member of ASME, EPB2 Material Standards, and EPB3 Nuclear Components. With that, please join me to welcome the seminar speaker, Mr. Gandy.
Thank you. Very nice to be back in NC State. Just to put it in perspective, I was here when we won our last basketball championship, national championship. So it's been a while. Thank you for having me here. I look forward to discussing advanced manufacturing and some of the things that we have ongoing for nuclear applications. First of all, is anyone familiar with the Electric Power Research Institute in the room? Anybody know who we are? Okay, a couple. All right, so the Electric Power Research Institute is headquartered in Palo Alto. We also have a major office in Charlotte and one in Knoxville. We are a nonprofit, about $450 million organization that does research on behalf of utilities around the world. I would say probably 25% of our membership is international, and the nuclear side is probably about 50%. We do research in anything that touches electric power, whether it's fossil applications, nuclear applications, gas, turbines, grid, environment, anything that pretty much touches electric power we're involved in. So that kind of sets a platform. Today, I want to talk about advanced manufacturing, specifically as it addresses small modular reactors, but we're also going to talk about a little bit about, as we move through this discussion, think about how this might also be applied to advanced reactors. I know many of you in the room are urgently looking toward a good career in the nuclear world and advanced reactors, and we are too. We're hoping this starts and really takes off, and I think it will. Lots of good efforts ongoing. So with that, let me go ahead and get started. So in the discussion today, I'm going to talk about some of the advanced manufacturing technology programs that we have currently ongoing with the Department of Energy. I manage 2 of those major programs and got a number of others that are engaged, but those are focused strictly on advanced manufacturing fabrication. We'll discuss powder metallurgy and hot isostatic pressing, electron beam welding, diode laser cladding. We'll talk a little bit about some of the heat treatment development work. And then I'll share with you a project that we're just kind of getting, well, we're in the 2nd year of it, that's looking at modular in-chamber electron beam welding to assemble large components. Again, as I start the discussion today, many of you are focused on advanced reactors. The project that I'm talking about is small modular reactors, but many of the technologies that we will discuss are applicable for advanced reactors also. So this slide shows a project that we have ongoing that is looking at small modular reactors. We're actually trying to build these two assemblies, a lower assembly, upper assembly, and a lower assembly at 2/3 scale. And that will allow us to produce something that's large enough for ASME to actually realize some of the technologies that are being developed here. The project is really focused on rapidly accelerating the deployment of small modular reactors. We're looking to demonstrate a number of manufacturing techniques that could be used by industry to reduce the overall development to around 12 months. Can anybody tell me how long it takes to generate a large forging for a nuclear application? Can anybody tell me where those are made? Okay, so most of the small modular, or most of the reactor vessels to date have been made in Japan, Korea, China. The US no longer makes large reactor vessels. So a lot of that's gone overseas in recent years. Very large forging, sometimes it can take 3 to 4 years to actually get into queue to actually be ready to build one. And then when you start building it, it might take you another 2, 3, 4 years. So it's a long process. What if we could do that in 12 months? What if we could eliminate a lot of the cost out of actually building those components? So these are the primary methods that we're employing: powder metallurgy, hot isostatic pressing, electron beam welding, and diode laser cladding to build these components. Again, these are demonstration components just to demonstrate the technologies. The arrows on this, the red arrows actually show components that will be manufactured with powder metallurgy and hot isostatic pressing. The blue arrows actually show typically forged components, and we'll continue working as forges. So I'll show you some of those in a moment. As we move to powder metallurgy and hot isostatic pressing. Who's familiar with powder metallurgy? Okay, I have some introductions to do on powder metallurgy. First of all, today the largest hot isostatic press in the US is about 65 inches in diameter. So that will not build this reactor. This reactor is about 10 feet in diameter. So we're trying to develop the technologies that allow us to build a much larger hot isostatic press to build these components in. So let me talk about some of the components that we've produced so far. So what is the purpose in using powder metallurgy and hot isostatic pressing? Powder metallurgy means you start with a powder, you basically put it into a canister or a can that's very close to the shape of the component you're trying to build or produce. You put it under extreme pressures around 15,000 PSI and around 2,000 degrees F, and it consolidates that powder. That powder creeps on itself and basically consolidates into a solid monolithic structure. What I'm showing here are some of the large structures that have actually been produced. There's a large bow body that's been produced by Rolls-Royce. You see a reactor coolant pump that's made by Framatome and Albert Duval. We've done a good bit of work on some fairly simple geometries initially, and you'll see some pretty complex geometries in a moment. And then this manifold up in the top has actually been made in a few different sections and welded together. But again, what it does is it allows you to eliminate a lot of the interconnections within some of these and the welds that have to be made. It makes them as a single monolithic structure. So if you think about the way reactor vessels are made today, they've got a number of welded components, a number of different things that are attached to them. What if you can make all that in one structure? And that's the goal of the project. This is one of the very first components that we actually made out of the project. This one's at 44%. And the reason it's at 44% is that's the largest vessel we have today available in terms of size. So this thing is, what have I got on there? I even got the size on it. I'll just say 40. Yeah, it's 50 inches in diameter. So it's about the largest that we could actually put into a hot isostatic press and make that component. This is one single monolithic structure. There are no welds whatsoever. The welds that you see around here are on the can or the capsule that sits on the outside of the powder as it's being consolidated. This thing actually shrinks over time as you put it into the hot isostatic press. May take you 4 or 5 hours, 6 hours to get to this size. But you can see we can make very complex structures with this technology. So that's why we focused on powder metallurgy and hot isostatic pressing. We've also manufactured the lower section. So let me step back to this is the lower assembly, and this is the lower head that I'm getting ready to show you. You see the upper head on the first one on the right-hand side. So the lower section of this, we're actually making in 2 halves. Now, obviously, that's not the way we would do this normally. But again, we do not have a hot isostatic press large enough to do that. So we're making it in 2 sections and electron beam welding it together and then going through a heat treatment to actually get to the final properties that we're looking to get to. So you see all of the fill stems and the vents that are coming off of that. It's where the powder actually is poured into the component. And then you end up with a component that looks like what we're showing here on the right-hand side. Now, as that thing is further consolidated, it actually goes into a hot isostatic press, and that's what the vessel is showing here on the right-hand side here. That's the vessel that it's actually sitting down inside of. Once it goes through the HIP process, you can see pretty good bit of distortion and movement of that. And that's where the technology, where you have to develop the knowledge basis and the modeling basis to actually arrive at that final component geometry and size. So we then take this and actually weld it together to another half, and we end up with a solid half. Now this is upside down right now. It would actually be flipped up. So this is the bottom section. So we've went through a lot of development. I guess I ought to describe one other thing here. So let me skip back again. So there's a transition section up here. And if you notice, we're again showing it as a red item. So we're doing it also with powder metallurgy. I typically wouldn't do that with Pmhip. I would do it as a forged component, but we're trying to demonstrate some of the technologies, and that is what you're looking at right here. That's one of the 5 sections that will be necessary to build that circular transition section. In trying to make this, we are using gas atomized powders. Those are air melted powders. They pick up a lot of oxygen in the overall process because you're making with an air melted process, as opposed to a vacuum inert process where you might actually do much cleaner atomization of the powders. So as we make those powders, we're making with air melt. We've picked up a lot of oxygen and issues. It has changed our properties, and that's one of the reasons that we're really going through a lot of the discussions here. Let me talk about this. First of all, if we're producing a powder using the air melt process, we take it through a vacuum annealing process in the canister. So this is actually in a canister. You take it through the vacuum annealing process, you can improve the overall toughness pretty dramatically by just vacuum annealing the powder before it's sealed off and actually goes into the HIP vessel. So we've spent a lot of time developing that. This thing is pretty large. It's about 4,600 pounds, and about 6 feet tall, and it's actually a little more than 5 inches thick. That's probably more like 7 inches thick in certain areas. So we've had to go through a lot of development. I'm not going to talk about some of that development. It'll be in the slide package. You guys can go through that. I simply wanted to introduce the concept of powder metallurgy and hot isostatic pressing. I've got a number of other topics I want to go through, but just wanted to jump right onto electron beam welding since we've only got a limited amount of time here. And if we have time, we can go back and talk a little bit more about that. So we're trying to make large components using powder metallurgy and hot isostatic pressing. That's the first advanced manufacturing technology that we're using. Hot isostatic pressing has been around for 40 or 50 years. First developed at Mattel in Columbus, Ohio. It's been used many, many times over the years. We are the first ones that are really taking it and using it for extremely large parts. So there's a scale up factor that we're having to go through to scale from something the size of maybe this computer screen to something the size of this desk or even larger. And it's all about properties. How do you scale to get those properties? We've shown we can control the overall distortion issues that you have, and as you're trying to model these things and come in with something that's very near net shape. You saw the upper head section already. What we're trying to do now is scale it and get the properties, and we've been working on that for about 3 years. We're close. We're not totally where I want to be, but we're getting close. So let's talk about electron beam welding. Anybody familiar with electron beam welding? Anybody familiar with welding, first of all? There we go. Okay, got that. All right, so electron beam actually uses an electron beam to melt the materials. You typically bring something together in a butt joint, so things are tightly close together, and the electron beam just walks down through it. Why would you want to use the technology? Well, first of all, it only requires one pass. You have no filler material associated with the process. You can minimize the weld heat affected zones, so you minimize any issues with changes in grain structure. And we've been able to demonstrate that we can produce large reactor pressure vessel sections basically around that full 10-foot diameter. We've shown that we can produce that in about 47 minutes. That's a significant game changer. Today, it takes about 2 weeks to make that weld. We can do it in less than 60 minutes, probably 47 minutes in our first activity. So that's one big game changer. Another big game changer is looking at inspection technologies, and we'll talk about that in a few moments. What you see here is a large chamber that we're working in, and the electron beam process has to be done in a vacuum chamber. So this is actually at the Nuclear Advanced Manufacturing Research Center in the UK. It's outside of Sheffield. Large center that's been set up by the UK government to do advanced manufacturing technology development. We've been working closely with these guys for about 4 years now. This shows one of the electron beam welds. This is normally done from overhead, but we're actually developing some technologies to do it from a horizontal position. This is one of the welds that we've actually completed on a full scale, almost full scale, 2/3 scale component. It's a little more than 6 feet in diameter, completed in 46 minutes. The total diameter is around 10 feet. So we think, 60, 70 minutes, we ought to be able to do this. Again, comparing that back to the fact that it normally takes 2 months to do, 2 weeks to do that type of weld today by very experienced, very competent people. You can actually see the electron beam weld as it's been put in place here. This is part of the lower head. So this is the lower head. This is a shelf that attaches to the lower head and a large flange. If you remember, as that was flipped upside down on the first slide I showed you, that's what we're kind of looking at there. So we're doing the assembly of this. This represents one of the welds. The head will actually be placed up here on top of this. So that represents another large circumferential weld. And you can also see the weld that kind of joins the two heads themselves together. This is part of the work that's ongoing at the Nuclear Advanced Manufacturing Research Center. It takes that lower head article that we've shown and actually then goes through and machines it and allows us to put all of that together and weld it together with the electron beam process. A little bit more on the welding. You can see where it's actually been completed here. You can see the weld here. This top part of it, which is actually the bottom part, will actually be done with additive manufacturing. It's a support plate, so it really doesn't, this lower portion really doesn't have to have anything but structural integrity. It's not toughness that matters there. The toughness and strength actually matter for the rest of the vessel. This shows a little closer view, the actual weld joint and then the actual weld that's been done here with this particular component. And then this actually goes to final machining. So a lot of big parts that we're working with, these aren't the biggest parts. If you look at a conventional reactor, you might be, well, for a boiling water reactor, we're probably talking on the order of 18 to 20 feet in diameter, maybe larger in some cases. For a pressurized water reactor, you might be talking 12 to 16 feet, somewhere in that range. These are, again, going to be at about 10 feet in diameter for small modular reactors. And then as we get to advanced reactors, that's actually probably going to collapse even smaller in terms of overall size. So that's another technology. That's a significant game changer again for industry. We are working with the Advanced Manufacturing Research Center, but we've got Babcock and Wilcox is working with us, Doosan, NewScale Power, the Welding Institute out of the UK, many other folks that are Rolls-Royce that are really engaged in the overall discussion and trying to implement this technology and take it forward. A third technology is diode laser cladding. So normally when you manufacture a component, a large reactor vessel, you will want to clad the inside surface of those components for corrosion performance. They're either clad with an Inconel, a nickel-based alloy, or probably a 308 or 309 stainless steel, which again gives them the corrosion performance on the inside surface of the vessel. Normally, we've used submerged arc welding or electroslag welding, which puts down a very large bead. It's all semi-automatic at best. So what we're trying to do is automate the process, and diode laser cladding enables you to do that. And it also enables you to put down a much thinner layer on the surface so you get less distortion overall. You can see a number of different computerized welds that have been done here, or clads that have been applied to the surface of this. What you're seeing here is actually one of the support structures that's inside of the lower head. So inside of that head, you've got to have support structures that support the rest of the reactor internals. So you can see a lot of the different welds that have been performed here. Again, this is being done at the Nuclear Advanced Manufacturing Center. There were probably 8 or so different programs that we had to develop to actually weld this component, but we fully automated the process. You could go out today and utilize that to clad an inside of a reactor. This was a very difficult, complex problem, but computerization obviously allowed us to do that. We've reduced the time to do this to about 24 hours from probably, again, about a 2-week cladding process. So that, again, is a pretty big game changer. Another big changer is we only used about 200 pounds of filler material on this. The small modular reactor that we're talking about will have enough surface area. Basically, it will be the same surface area as 2 Olympic swimming pools because it's clad inside and out. So by reducing that overall amount of filler material, you're reducing cost, you're reducing the overall amount of time that you're trying to apply that cladding to. So that's 3 of the technologies we've worked on. Another technology that you look at and say heat treatment. What the heck can you do in heat treatment that is revolutionary and can be something that can significantly help industry? We've been focused on primarily looking at how we can eliminate the weld. Basically, once we've done electron beam weld, if you think about electron beam welding, we're not putting any filler material in it. So you don't have any reasons, if you've got filler material, one of the issues that you may have over time, depending upon the filler wires that you've used, is embrittlement of that structure. Many of the early reactors that were built in the US used what I would say were somewhat inferior filler materials in terms of they had tramp elements like phosphor and sulfur and copper, which ultimately led to embrittlement of some of those. We have to watch those very closely. We know where those are at and we know what the life of those are. What we're trying here to do, though, is because you're not putting any filler material in with the electron beam process, you go through a heat treatment situation where you can actually essentially remove that weld. So if I remove that weld, do I really need to inspect that at 10-year intervals? Normally I inspect every weld in a reactor vessel in 10-year intervals. Will I have to inspect this now? So the question is, can we develop this for very large components such that we can heat treat them without distorting the component? And then we go to the NRC and basically get them on board with helping us to eliminate inspection of these components, because this will now be one solid structure with no weldments in it. Can't see the weldment, where is it? So that's what a lot of this technology is focused on right now. We've done a lot of heat treatment work to understand those. And essentially we've arrived at working at 875C, still providing good properties. You can see the trail off here, but we're showing good properties in terms of toughness at around 875C heat treatment. That heat treatment involves a homogenization, a quench, followed by a hardening or a normalization of the material, another quench, and then a temper. So it's reasonably complex. You got to think about this again in large sections that we're working with. How do you heat treat those without distorting them? So we've been working with Sheffield Forge Masters, a large forging house, to actually go through some very complex analysis on these and modeling to understand what the stresses are on those and what types of distortion we might be seeing. And we basically said, yes, we can do it. We're now in the phase of taking this. We've done one smaller section like this, which represents kind of a head that we would be working on. One shell section we worked on. We're now moving it to a little bit larger size with the full intent of one of these days we can do this at full size without any issues, any significant distortion. So this is a big deal. Large forging house, lots of heat, lots of issues ongoing in the large forgers that I'm not typically engaged with, but this is a pretty complex problem. So again, this kind of takes me back to this component. Again, the lower head, the shell section, these two flanges, and then this transition section. So big components. We've been able to show that, again, in a modeling perspective, we've been able to demonstrate that we don't think we're going to get significant distortion. We've done it at smaller scale. We're moving to 2/3 scale and then eventually full scale. A lot of this work would then support a code case that would go in front of ASME boiler code to allow you to utilize the technology. And then the NRC would have to come on behind that as a regulator and support the use of the technology. So that's 4 technologies I've talked about. One of the other big projects, this is an entirely separate project in and of itself, is looking at that large chamber you saw at Nuclear MRC is not large enough to do a full-size small modular reactor. Even a small modular reactor might be on the order of around 35 feet in total length or height. So that vessel section, that chamber is actually not large enough to do the heat treatment and or the welding in. So we're actually looking to set up a vacuum chamber that's a modular vacuum chamber that'll allow you to do this process. So let me walk through that in the last 15 or so minutes here. So I showed you this a few minutes ago. This is the large weld that we did in 47 minutes. What if we could actually build a chamber that you could take apart, put back together, depending upon where the elevation is of the weld that you're trying to make? So this one only has 2 welds in it, it's represented here. So let's imagine this gold section is the reactor vessel. So this is the shell section. Here's that large flange, kind of what you see here. So that's the first elevation, but you need to get to this next elevation too. The way to do that is actually you pick this whole entire vessel section, or pick the whole top of this off. So the green module, the magenta module, and the lid here would actually come completely off. You'd stick in another spacer section, such as you see here, and then put those back on top, which gets you to the elevations you need to make the next weld. Does that make sense to everyone? So basically, it's just stack and destack till you get the elevation of this electron beam gun to the location that you need to do the weld at. So we've been working on that. This was a concept we had. We're working very closely with BWXT and the Navy actually to do this work right now. The Navy's very interested in this, and you can think of why they might be interested in large diameter vessel applications. So we've been trying to do a lot of modeling to develop that. Again, the green section here in this case shows where the shell section would be. We've done a lot of development around how this platform looks. We're into the second year of this project, and the project's really taking off. We're actually making lots of large components. We're making these large modules for the overall welding application now. We've already manufactured the electron beam gun that you see here in this, and I'll show you a picture or two of those in a moment. A number of the controls are already done. Lots of things that we need to develop in this project though. So we've been working on developing some of the pumping capabilities. Now you think about this thing, it's 35 feet high when it's all stacked up. I can't sit there and wait for days for this thing to pump down to 10 to the -3. It takes a long time to pump that. So we've got capabilities based on all of our design work. We think we can pump it down in about 2 hours. So that's what we're working toward right now, large pumps in terms of what we're trying to manufacture here. This kind of shows some of the overall equipment. There's the vacuum chamber. This is a chamber that we've actually set up in Connecticut with a group called PTR. It's a smaller chamber. We're trying to test out all of our equipment and make sure everything works. Our big electron beam gun, we want to make sure it works. We're using a different style gun than what we've used in the UK. It all had to be developed domestically because this is a Department of Energy funded project. So we're developing it with our counterparts in Connecticut. You see some of the transformers and high voltage packages. This is the electron beam gun itself. It's about 1,000 pounds. It generates the large electrons that are necessary to go in and actually make those 4.5 inch thick welds that we were talking about. This is just a big slide package that's sitting on the outside of a small vacuum chamber right now, again, to test out the technology. This is what the technology will look like when we're through. I mean, if we built this thing to full size, this is what it would look like. Right now, our demonstrator is only going to be 4 modules tall, but it will be full diameter. This will be about 12 feet in diameter, which will allow us to do a 10-foot diameter section, a weld inside of that. You can see the green module here. That's where the electron beam gun sits on the outside of it. Again, a spacer module and a lid. So you saw the original concept, original idea of how we started this thing. This is kind of where we've gotten to at this point, and we did final design review, and I've just let the contract go for manufacturing these modules and some of the support legs and other things that are necessary around this. When this is done, which I think will be probably the first of 2023, we will start welding and do a number of welds with BWXT out of Ohio, and we'll start then to make large reactor vessel weld sections with that technology. The ultimate goal of this is NuScale Power will look to use BWXT to manufacture many of their reactor vessels themselves. So this is real time, something that's going to be used. Lots of industry initiative around this, and lots of industry interest, not only domestically, but internationally. There's a lot of interest around this. I mentioned Doosan a minute ago. Doosan's also working with us here in the US to try and perfect some of this technology. Doosan's obviously from Korea. they will be looking to utilize the technology for manufacturing some of their components too. So lots of interest in trying to take the technology forward. Lots of sections that go into putting this thing together. So it's not just what you saw on the outside. These are full scale or to scale size components. Large rotary table that sits in the center of this thing. We have large rotary tables already today for doing a lot of machining processes. That's what this will be, but it will be inside the vacuum. Believe it or not, you have to use different greases and different things as you put them into a vacuum chamber too. So lots of learning on that overall process. Just a couple of the other things. This is, again, we hope to be welding and much of it together in by the first quarter of 2023 and actually doing welding in third quarter of 2023. So I've showed you a number of different technologies. I haven't talked about additive manufacturing. We've got a number of projects ongoing in that area supporting both AS&E applications and trying to bring the technology forward. I know many of you have been involved in additive projects. You already had made individual parts, but when you start making large pressure retaining parts, say I want to make a valve, you got to meet certain properties, you got to meet certain criteria, and you got to be able to do it repetitively. So we've worked a lot with people like Oak Ridge National Labs and Westinghouse and Rolls-Royce and others to bring some of that technology forward. We're close. We have a code case in front of DOE right now, and actually there's a second code case that's followed right behind on directed energy deposition additive manufacturing. So there's work ongoing there. You've seen some of the other things that we're working on here in terms of the project that's shown in the center and then the project that's shown here. The other thing I didn't talk about is adaptive feedback welding. Many of the technologies, many of the components that you find in a nuclear power plant are either welded together with manual stick welding or they're welded together with gas tungsten arc welding. Gas tungsten arc welding, when I started my career back in the mid 80s, was using semi-automated gas tungsten arc welding processes. Today, it's using semi-automated gas tungsten arc welding process. Why haven't we automated the process? That's what this adaptive feedback project is about. How can we sense the weld puddle that's actually being put down, understand when we've got issues, make corrections on the go, and actually do a fully automated process. So that's where that project's going. Again, many different activities in advanced manufacturing. I know this hasn't been deep technically. That was not my intent today. There's many deep technical portions of this, but what I wanted to show you was there's a broad area in terms of advanced manufacturing and lots of different things ongoing in industry. And I've only captured a few of them. I mean, there's many things that are looking at advanced alloys and how do we deploy those advanced alloys? How do we work in advanced reactors and advanced reactor space? But what I wanted to try to give you a flavor of was some of the advanced technologies that we're currently working on. And with that, I really won't go through the summary slide here. I think you can read that. We talked about 4 or 5 major technologies that industry is going to utilize. I guess at this point, we can open up the table for some discussion. I might be a little short on time here.
Thank you very much. Okay, open the floor for questions. I saw some chat message. I'm going to read this from here. The items made with the Pmhip result in a crystalline matrix, or are they amorphous?
Yeah, that's a good question. Does the Pmhip process result in a crystalline or an amorphous structure? It's a crystalline structure. One of the reasons we're looking at it is because when you put it in a hot isostatic press, you put a powder in it and it consolidates, it results in a very uniform equiax structure, basically an equiax structure. So you can push sound through it easily from whichever direction you're trying to look at it from. So we can use ultrasonic processes to understand, do we have anomalies or flaws in that component?
Okay. The second question is, do the Pmhip manufactured materials have different resultant tensile stress, thermal conductivity, and DPU resistance values relative to traditional manufacturing technologies using the same materials?
Good question. So from a tensile standpoint, we're able to consistently produce really good properties. We struggled a little bit with ferritic alloys, with low alloy steels, because they tend to pick up oxygen, and the silicon and combines with that oxygen, goes to the grain boundaries, and you end up getting reduced toughness. We've been working on that. I think we've kind of got it figured out. We're doing a process called vacuum annealing to get rid of some of the oxygen out of the powders themselves. You could go to a VIM atomized powder, you can also get rid of it. I'm trying to use the least expensive process, develop the technology around that. If I go to VIM atomization, it's very expensive. I use air melt atomization, I can get there. So we can get the properties. I'm pretty convinced of that. In terms of DPA, we have some work ongoing right now where I have powder metallurgy parts and electron beam parts at the ATR at Idaho National Labs actually being irradiated and being tested. The irradiation is done. We're in the process of testing. I'm working with Purdue University right now to get some of those. Janelle Wary, you guys may be aware of her. I'm not sure, is kind of leading some of that from Purdue.
That was a great talk, and I have many questions, but I'll ask just two.
Okay.
First, you mentioned about vacuum annealing. So if I remember correctly, like it has a problem that because of the low conduction, that the surface gets really annealed, but the center shows slightly different microstructure than the surface. Did you get this type of problem?
Yeah, and I didn't, let me step back here. Can we? Just go easier this way. So we've done a number of tests on components, trying to understand, can we remove residual gases out of the vacuum chamber itself? The diagram that you see here on the right, we have a 20 by 20 by 10 inch thick component that we've heat treated, or we went through the vacuum annealing process to try to get rid of any moisture, any residual gases that sit inside of that. You can see the tan line here. That actually represents a line, a location where we buried thermocouples into the center of the component to understand what were we getting the temperature first, and secondly, can we actually measure residual gases coming off of that. You look at this, we went out to almost 28 hours before we actually arrived at temperature where we thought after about 6 or 8 hours we were getting the temperature. So we were not fully getting to that annealing temperature to get rid of residual gases. Hence, they stayed, we still had oxygen in the part, and our toughness was much lower. We were able to show at different locations, elevations in one of those sections, that we weren't getting the right temperatures. So again, it affects microstructure, it affects oxygen content, it affects toughness. Hope I answered. That was a long answer for a short question.
Yeah. And second is, you showed that you are doing a lot of heat treatment for its hard solution solution hardening, and then followed by normalizing and tempering, which is kind of necessary. But that creates a scaling problem, like when you solution scale forms and then others, so that affects the dimensional tolerances, that you won't end up with the same thickness as you started with. And in your words, like it creates a lot of distortion as well. How you tackle that?
Well, typically you're going to make this thing at least a half an inch thicker than you would.
Just start with hard.
And then machine out of weight. If you think about a forging is going to be thicker too and be machined. And that's one of the issues with the particularly with the upper head, there's a lot of machining to take that large forging chunk down to a smaller part. We're trying to eliminate some of that machining work too.
This is right.
Yes.
The question is, are these technologies commercialized or is it case for this stuff?
We are looking to commercialize many of these technologies. We are not there yet. I think the electron beam welding will be the first that comes forward. It's already recognized by ASME as something that can be applied for large power plant components. Powder metallurgy, I do have a code case for 316 nail stainless steel, but I don't have one for 508 in place yet. That's part of this big project. So it's different stages that each of them will come forward.
So there's a lot of processes here that are impacted. Do you foresee, or is this kind of too crazy to think about, doing a good chunk of these steps the same kind of chamber environment, make kind of one-stop shop, so to speak, that processes are? Do these really need to be in separate?
They really need to be in separate processes. Now, there is an electron beam process that TWI, the Welding Institute, is working on in the UK right now. That's a smaller chamber that actually follows around the weld. Been working on it for a number of years. We're not quite where they need to be, so we kind of opted to go this route. Hopefully, both of them will get there. What I'm hoping for, to see. Yes.
Are there thickness or material limitations to electron beam welding?
We have shown electron beam welds that we've developed up to 8 inches at this point. I think that's probably about as thick as it will go at this juncture, but you could go at it from both sides if you wanted to. So realistically, probably not. I know that some rotors have been welded with the technology. You know, and a rotor, depending upon the size, whether it's a fossil or a nuclear rotor, can be pretty thick. So, yeah, it does have limitations, but I'm not sure what those are at this juncture. We've done 8 inch, which is pretty darn thick part.
Are there any even less common materials that just don't respond well to electron beam welding?
No, it pretty much welds anything. I mean, from titanium and nickel-based alloys to steels. I've not run across much of it yet. Join. Electron beam welding has been used on your automobile, and the crankshaft or many of the different parts on your automobile probably has electron beam welding utilized on it. The issue is those are very thin sections. We've moved it to 4 3/8 inch, 110 millimeters. Again, we probably can take that further if we need to, but that's the size of the new scale reactor design right now is 4 3/8 inch. Yeah. Oh. Put glasses on here where I can. Has liquid nitrogen cold welding been considered for a similar process? If so, what makes it less feasible? Liquid nitrogen cold welding, what is that? I'm not sure what they're after here. Somebody's going to give me a little more information on that one. I'm not sure how to answer that. Next one is, do we accept any difference between the behavior of the heat affected zone for electron beam welding and any other technique? In the special case of nuclear power plant decommission, that's the second question. Do we accept any difference between the behavior of heat affected zone, electron beam welding, and other techniques? The heat affected zone in electron beam weld is going to be very narrow. It's typically when we look at determining the toughness of a weld, we do Sharpie impact specimens, which have a little V notch to locate in the heat affected zone, or you use fracture toughness specimens to assess that. There's not really a wide enough zone to do sharp impact specimens. We do have a lot of testing ongoing that's looking at fracture toughness to understand the properties of that heat affected region, as well as the center of the weld, as well as the base material. So a number of different techniques that are utilized to do that. I won't say both techniques, looking at conventional welds versus electron beam welding, it's a whole lot different. Still have to meet properties. Still kind of similar testing is required today.
Last one.
All right, in the case of nuclear power plant decommissioning and when we need to dismantle some of the components, do we need any special arrangements to deal with the AM components, especially as they are radioactive? We decommission most of, when we're decommissioning, we can go through processes that basically clean most of the fixed contamination off of these components and get them down to where they can actually be processed or stored in for long-term storage. Decontamination processes today are pretty darn good. It won't take all of the irradiation out of some of these, but certainly we can get them down to where they can be stored pretty readily. I don't think there's any difference from an advanced manufacturing technology versus the conventional technology that's used today for the decontamination.
All right, we have an explanation for the cold welding from aircraft manufacturing. They previously used the geometric contraction of the material for fitting components together while cooled, so that they would be effectively welded in place when returned to room temperature.
Yeah, so we've not tried any of that at this point. I'm not sure that's necessary from our side, but maybe I need to look at it a little bit more. No, we've not done anything in that area.
I've got a question as well.
Yes.
For the modular in-chamber EPW, have you considered using any of these advanced manufacturing techniques to manufacture some of the parts for the chamber?
Yes, we will be doing powder metallurgy parts that we'll be assembling. Many of the components that you see will actually go inside of that chamber. Some new technology. Definitely. And another question.
Yeah, a bit of a clarification about electron beam welding. Obviously, there's no filling material, so you don't need V-notchers like they just make two surfaces flush with electrons and then
Straight surfaces, and electrons go right through the center of it.
so that max distance is just the furthest electron is going to travel and correctly melt the material.
Yeah, so let me go back to that one picture of it. If I can get it back there. You can see the electron beam weld here at the top. That's about 4 inches across there, I think. That's a pretty thin weld that's been butted together, and essentially it just melts what's in the center of it there. There are laser processes that we also work with that we've had mixed results on. They're not nearly as effective right now as electron beam weld.
All right, any more questions here or on Zoom?
Again, wasn't a very technical discussion. Trying to introduce you to a lot of different technologies here. We can go as deep as you want to go into any of these. I'm more than happy to do that, but I thought it was more important to expose you to a lot of different things we're working on.
All right, last chance.
Since it's already there, you mentioned the reduced inspection. Have you tested the products on the radiation environment and tested the alignability, any issues that came up different from traditional methods?
So as I mentioned, we have both Pmhip components and electron beam welding components at the ATR up in Idaho National Labs right now being exposed to radiation and being tested. We don't know what the long-term effects of those are. What we're trying to do is develop the technical data that allows us to put some of these in service. So at this juncture, I don't really know what that might be.
All right, let's name the speaker one more time. good.